Let's get started. So first of all, I hope you all had a good spring break. Hope you got some rest in, got some recovery in, ready to sort of finish up and end off the semester. Uh, I'm still not doing amazing physically. A little better than I was on Tuesday, at least. I should be more cogent than I was for the Tuesday group, hopefully, for you all today. But still not doing great. Mainly just at this point, just the position of sitting at a computer is sort of causing some neck pain. So I'm probably gonna just try to move us along reasonably quickly today. Just try to sort of get through everything a little bit. I'm improving, so hopefully by next week I'll be back to normal. I'm hoping, and we can sort of hold class like we normally would. Um, I haven't really done any grading for like a week and a half at this point. So I haven't really even started on your last exam, which I'm really sorry about. I think what I'm probably going to do to sort of make up for it is I'm probably just going to make the upcoming exams a little bit shorter so that I can get caught up with the grading a little bit as a result, and also have to do less sitting to try to get them ready to go. So there'll be an exam this weekend covering the chapter 6 material that we talked about before spring break. And then what we'll talk about today, it'll probably be, my guess is 22, 23 points, something in that range. So a little bit shorter than normal. And then, yeah, my pop may be the same. The final was already going to be pretty short, actually. But yeah, that's probably what we'll do the rest of the way. So does anyone have any questions just about anything with the course or anything before we get started for the day? Remember, you can unmute yourself, and you can also send me things through the chat too. All right, awesome. Then, like I said, I'm going to rely a lot on the videos for this day. I'm not really going to go over much of the sort of background with any of this stuff. Let's just start working our way through some problems. But don't worry. Like, if you have a question, ask it. I would have just canceled class if I couldn't handle that. Like, if you got a question, ask it. You know, I want to, like, that's why we're here. So don't feel like you need to hold anything back for my sake. All right. So let us begin going to the activity. All right. So this week we're going to talk about what are called statistical inductive arguments. So they're still inductive arguments. We're still not reaching certain conclusions. We're still less than 100%, or 0%, I suppose. That's also certain in a different way. Confidence. But unlike in probative inductive arguments, where what we're given is basically reasons to just kind of think that a conclusion is true, what we're given instead is like, how likely is it that the conclusion is true? So it has a statistical percentage. That's the sense in which we're looking at statistical arguments. It won't always be a literal number for this kind of argument, right? Something being extraordinarily likely, that's not like 95% or whatever, right? That's not a number, but it's sort of standing in for a number. It's standing in for a percent of some sort. So don't worry if you don't see a specific number. What matters is that we're sort of talking about sort of like what proportion of a group has a property. That'll be the marker that what you're looking at is statistical. Our two kinds of statistical arguments we'll talk about today are statistical syllogisms and inductive generalizations. Those are what we're going to look at. We're going to actually talk about them reasonably differently. Statistical syllogisms, basically, I'm going to be looking for like a sentence on the exam. Pretty much the exam questions are going to look like exactly like the questions we're going to talk about today. And yeah, there's not going to be that much you'll need to write compared to some of the other problems maybe that we've been doing. A good sentence or so will do it. The inductive generalizations are more like the earlier problems in the semester, where we're talking more like a good paragraph will be what are needed to sort of fully address those questions. For the statistical syllogisms, let's just start talking about them. You're going to basically just be tasked to sort of evaluate if you're looking at a good or a bad one, basically. These are very common kinds of arguments. You yourself rely upon these kinds of arguments all the time. Indeed, you probably don't even think of them as arguments. That's how sort of common you are and how commonly you rely upon them. I was thinking last night, actually, when I was getting, or actually before Tuesday's class, when I was getting ready to teach. Here's a weirdly, us relying on memories of things is actually a statistical syllogism, right? It's sort of like weirdly like, yeah, most of what I remember is probably true. I remember this happening, so therefore it probably happened, right? Because you know not all of your memories are true. We know we have sort of like memories that are sort of made up or whatever, right? But you're sort of like, well, most of what I remember is true. So I remember this thing happening, therefore I'm going to assume it actually did happen, right? So this will be a case where, again, the goal is not going to be to learn some brand new thing. It's going to get better at the skill you already have, right? Get better at making this kind of argument, recognizing this kind of argument, and then maybe get a little bit more precise about two different ways these kinds of arguments can go wrong. So there's going to be basically 4 options that you'll have on the exam. That's why you really only need like a sentence or so. So one thing you can say is that when you're looking at a statistical syllogism, the conclusion is indeed very likely to be true. Right? And, very likely, that's a little bit vague. So let's just say that means something like greater than 75%. I'll either give you a number on the exam or some verbal thing that should be pretty obvious. It shouldn't be any sort of borderline cases. So if I said overwhelming majority of people, that would be a very likely to be true kind of conclusion. That sounds more like a 75%. There won't be any kind of borderline cases unless there's actually just looking at numbers. Second option, the conclusion is somewhat likely to be true. So still a strong inductive argument, but you're a lot less confident, right? The conclusion is only 75% likely to be true, but still it's greater than 50%. So something in that range. Again, it could be not numbers, but again, it should be pretty obvious if it's the really very likely or the somewhat likely option. So both of these first two are good inductive arguments, right? The first would be a stronger inductive argument. The conclusion is more likely to be true, but both of them have a greater than 50% chance of being true. The second two are bad bad statistical syllogisms. The argument's gone wrong with both of these. So one other conclusion you can come to is that the conclusion is unlikely to be true, right? It's less than 50% chance that the conclusion is the case, right? And so therefore a weak argument, less than 50%. The other possibilities you come to say that the argument commits the fallacy of incomplete evidence, which means that the statistical result is just useless and you don't have any idea how likely the conclusion is to be true on the basis of the argument. One of the things we'll try to really focus on today is distinguishing this third and this fourth option. We'll try to get really good at seeing how those are different. And I've got some examples in the activity that I hope will help. But for right now, at least, let's just start with this sort of straightforward one. There's no trick to this problem. Work on number 1 for a few minutes, or for 30 seconds maybe, and then we'll go over it. All right. So here we have the world's, at least I hope, worst jail. I hope there's no jail that is arresting people more unjustly than this one. Right? All right. We've 501 of the 1,000 people in the jail are guilty of a crime. That's terrible. Right? All right. What do we know about Joe? We know that Joe is in the jail. That's it. We don't have any additional information about Joe. So all we know is that he does indeed fit within this sort of statistical category that we've been presented. Right? It sort of matches him. Not a trick question here. How likely is it then that Joe, based on the information we have, that Joe has committed a crime? It's somewhat likely, right on that borderline. Right? It's exactly 50.1% chance. Right? And so, okay, if you were forced to guess, it would make more sense to guess that Joe is guilty than that he's not, right? I mean, there's a less than 50% chance that he's not guilty, right? So it would make more sense to guess that he is, but you'd be really unconfident about that, right? You wouldn't feel good about your guess. It would just be the best guess you'd have available to you given the information, right? And so in that sense, then, if it is the rational guess, you're looking at a strong inductive argument. That's how I sort of think of inductive arguments, right? Like, are we making the best guess that we can given the information we have? The best guess you can make given the information available to you is that Joe is somewhat likely, right, to commit the crime. But again, you're not confident. You don't feel good about this guess. Contrast that in the case of number 2. So take a quick minute, look at number 2. Right? Again, no trick here. Basically the exact same problem. It's now just it's a much better jail, a much fairer prison. That's really the only difference. We still don't know anything else about Joe other than that he is in the jail. That's our only information. And so as a result, Joe, this does seem as if it's an applicable statistical information to Joe. The information applies to him. So in this case, we would conclude, right, that the conclusion is very likely to be true in this case, right? There's a much higher percent chance based on the improvements of this jail or improvements of the prison system or whatever, right? That the fact that the person is in jail means that they are guilty of something, right? So again, unless you had some other information about Joe, you could be reasonably confident in your prediction, right? That Joe is guilty of the crime, right? As a sort of result of this statistical information, right? So it's a useful statistic. It applies to Joe. And it does indeed suggest that there's a much greater than 50% chance that the conclusion is true. So here we'd have, again, a strong inductive argument, even stronger than the one in number one. Right. How are we doing so far? Any questions on anything so far? All right. Now let's go to number three. Let's get more complicated with it. All right. So my guess is that even before you took this class, you would have thought something's a little bit funky here. Something seems a smidge off. And indeed, you would be right. Something is off here, right? So first, let's just look here. We have most people from the People's Republic of China do not speak English, right? So most, again, the fact that that's not a number, that's not a problem, right? Most sort of stands in for some kind of statistical thing. It probably just means something like greater than 50%, something like that. So fine. Most people then from People's Republic of China don't speak English. Fine, right? Therefore, the newly appointed ambassador from China to the United States does not speak English. What's different here? We know more information about this individual beyond the fact that they're just from China. Right? We know other stuff about them. What do we know? Well, we know they've been appointed as ambassador from the China to an English-speaking country. Right? I mean, if I had said to Great Britain, this probably would have just as much committed the fallacy, or Australia would have just as much committed the fallacy. And why is that information pertinent? Well, because we have every reason to sort of suspect that ambassadors to a country are way more likely than the average person within a country to speak the language. Right? So an ambassador to an English-speaking country is way more likely to speak English than any old random person. Similarly, if we flipped it, the ambassador from the United States to China is way more likely to speak Chinese than the average person in the United States is. Right? As a result, the statistical information that we're given, true enough, I mean, I didn't look, but I'm assuming this is true, right? It's just not relevant or useful information to figure out how likely it is that this specific ambassador is going to speak the language, right? Think of the fallacy of incomplete evidence as they did their math wrong. That's basically what both of the fallacies we're going to talk about today. That's what they both sort of mean. They did the math wrong, right? They didn't calculate the percentage of how likely it is that this person is or is not to speak English because they didn't include all the information they know about the person. Right? And some of the information they left out is indeed relevant to whether or not the person will or will not be likely to speak English. Similarly, think back in number two. If I change this to Joe, a security guard, is in jail, all of a sudden I think you'd want to say, wait a second, this is probably not super useful information anymore, right? Because a security guard is probably dramatically less likely to be in jail because they've committed a crime rather than they're in jail just as a guard within the jail. Right? And so again, then this change would make it so that the fallacy of biased statistics has been, or fallacy of incomplete evidence rather, sorry, the fallacy of incomplete evidence has been committed. Right. How are people feeling here with this fallacy? Is it making sense? Questions at this point? Note that I want to emphasize, just because this is something I see students sort of mess up sometimes. The fallacy of incomplete evidence only occurs with statistical syllogisms. So don't talk about it in other kinds of arguments. Say inductive generalizations. Inductive generalizations will never commit the fallacy of incomplete evidence. Similarly, the other fallacy we're going to add today, the fallacy of biased statistics, that only occurs in inductive generalization. So never tell me that a statistical syllogism commits the fallacy of biased statistics. This is only relevant in the context of a statistical syllogism. So good. All right, let's go to number 4 then. All right. Again, my guess is you read this and you kind of say, yeah, something seems wrong. Something's off. So the reasoning has not gone properly, right? But what I want to emphasize and note is the difference between how 3 went wrong and how 4 went wrong. So 4 is just a case where I think we just want to say this conclusion is just unlikely to be true. Right? There's a less than 50% chance, indeed only a 10% chance, that the conclusion is true in this particular case. If you were, we don't know anything else about you, quote unquote, in this problem, that would make you an exception to this general rule, if you want to think about it that way. Right? Whereas in this case, we do know something about this ambassador that would make him or her an exception to this rule, namely that they're an ambassador. Right? That actually would make them kind of an exception to the generalized rule. Right? This argument does not commit the fallacy of incomplete evidence. It's not that we don't know, that we're not including in our statistics something about you, quote unquote, so that's relevant. The mistake that's being made here is that a perfectly useful piece of statistical information, we're just deriving the wrong conclusion from it, right? And to sort of prove that, look at 5 real fast. 5 is the same exact thing, just reaching the right conclusion. Right? The right conclusion here is that you should not plan to get in. That is, statistically, you are very unlikely to get in, right? We can use this statistic to arrive at the correct conclusion. There's no problem with how it was calculated. It was calculated correctly. In 4, it was just used improperly. It just wasn't used to reach the right outcome. This statistic here, most people in China don't speak English, is just not really relevant, or it's very minimally relevant. It's not useful statistical information to figure out how likely it is that this ambassador is going to speak the language. And so that's the difference between these sort of 2 different ways of the argument going wrong. Both of these are bad statistical syllogisms, but they're bad in kind of very different ways. And recognizing the difference is sort of the big thing that I wanted us to get from talking about these. So how are people feeling with how 3 and 4 are different? Any questions, concerns, thoughts, comments at this point? All right, then let's do one. We're good so far. Let's do one more statistical syllogism. Another weird one. Right. Again, my hope is that you read this and you're like, this doesn't make any sense. This seems super backwards, right? And it's actually a super weird argument. Even let's talk right through it. Again, we don't have a number, but that doesn't matter. The fact that there's no number sort of beside the point. Overwhelming majority, that's clearly more than 75%. It seems like, right? That's a big number. Right, and indeed, this is true, I suspect, right? So the overwhelming majority of people present within a courtroom are not guilty of the crime of murder. Right? That is indeed the case, right? Because who's present in the courtroom, right? We've got maybe the jury is present. We've got the audience is present. The judge is present. The prosecutor, the defense attorney, maybe they're journalists present at the trial, right? And yeah, there's very little reason to think that any of those people are guilty of the murder that the trial is investigating, right? True enough, fair information, right? But we know something about the defendant in the case that makes them different from everyone else who's present within the courtroom. And what do we know about them? We know that they're the defendant in the case. That's what we know about them, right? And so as a result, we just said the defendant in a trial is far more likely to be guilty of a crime than other people present within the courtroom. Right? And so as a result, then we've got the fallacy of incomplete evidence. This is just kind of irrelevant. It doesn't matter how many, what percentage of people present within the courtroom writ large are or are not guilty of a crime. That's just beside the point. Now, does this mean that the defendant is guilty? Nope, doesn't mean that either, right? When we say that an argument commits the fallacy of incomplete evidence, we're saying that it gives us no useful information. That's the difference which in 4. This percentage does give us useful information. The right answer is just the opposite answer, right? There's no useful information given by this argument to tell us whether or not the defendant is or is not guilty, right? It's not helpful. Maybe we could do something like maybe figure out what the percentage of defendants in a murder trial are guilty or not, and maybe that would at least be relevant. It might not even be legally relevant because the standard is maybe higher than just guess in law, right? But it maybe be somewhat relevant. But this information is irrelevant to figuring out where the defendant is on. Again, the math hasn't been done properly. We did not calculate the percentage of how likely the defendant is in a correct way or in a useful way. So how are we doing here? That's the last of these statistical syllogisms I was planning on going through. So does anyone have any questions about any of these examples, about the fallacy, anything? So remember, all I'm really looking for is like a sentence, right? If you're just saying that the conclusion is sort of very likely to be true, you could just sort of say that basically with maybe just list the percentage or something, right? That's enough there. Maybe a little bit more for the fallacy. You're saying it's the fallacy, you just have to tell me what evidence is not being included. Right. But again, that's basically a sentence still, right? That's not much more than a sentence. So yeah, unlike a lot of the other problems we've done, you don't have to sort of go on at length for these problems. All right. Good here. All right, then let's jump to the inductive generalizations. Here, there's a lot more to say. So this is more like the previous problems where I'm looking for a good paragraph for here. And part of the reason for that is that before you actually answer the main question again is just going to be evaluate the argument. Is it a good or bad argument that you're looking at? I'm going to ask you to do a bunch of sort of intermediate questions along the way. And the goal of these intermediate questions is just to sort of help you identify the relevant things that you'll need to look at in the course of actually evaluating if you're looking at a strong or weak argument. So that's why there's sort of these many steps. Basically, these first 3 should help you answer the 4th. The 4th is the one that actually matters. The 4th is the real question. Are we looking at a good or bad inductive generalization? Unlike the statistical syllogisms, you do inductive generalizations in the course of your daily life, right? But you usually don't do them in a statistically rigorous way, which is why they were earlier in the semester, we actually characterized these as a kind of probative argument. And that's for how you do them in the course of normal day-to-day life, they more are probative arguments than statistical ones. When we're talking about inductive generalization in a statistical sense, what we're really talking about things are like massive opinion polls, right? Or maybe medical testing, right? Things where we're doing sort of exhaustive kinds of studies. And so unlike some of the other things we've been talking about, you don't really do this kind of argument, at least in the way we're going to talk about it, in the course of your daily life. What you do encounter these arguments, though, in the course of your daily lives, right? You encounter opinion polls, or maybe if you pay attention to politics, you encountered predictions about who was going to win the last election or whatever, right? That kind of thing that you're encountering there are inductive generalizations. So our goal here is going to be more just gaining kind of fluency in how to recognize these kinds of arguments when we see them, and then understand kind of what's going on within them, and get some basic familiarity of sort of really egregious mistakes that you can make. In general, you would have to take a math class to make it so you could really do this kind of argument on your own well. You could easily spend an entire statistics class just talking about how to do this, because the crazy thing is that you can calculate a lot with these inductive generalizations. You can calculate exactly how large this sample size have to be. How likely is it that there's a sampling error? What should the margin of error be? Like, all of that can actually be calculated pretty precisely, actually, but that's a math class, and we're not doing a math class. So our goal is fluency. So with that in mind, the 4 questions I want you to sort of work your way through. First, identify the sample group and the overall population within the argument. So that's the first thing. The reason why I think this step is really important, it might seem sort of redundant or sort of obvious and not worth stating, but I think it really is. Because the only question you should be asking yourself when you're evaluating the argument is how well does the sample group represent the overall population? That's really it. That's the only question to be asking. So being really precise about what the sample group is and really precise about what the overall population is kind of the first necessary step. You can't say how representative is the sample group to the overall population if you haven't gotten the sample group right, if you haven't gotten the population right, or if you're not sort of characterizing them correctly, how they're sort of made up. Second step, similarly related, describe the sampling method. Basically, the question here is, how was this sample group made? What was the technique used to create this sample group? Again, that's going to be really relevant for telling us how representational the sample group is of the population. So these first two are basically just describing things that the argument already says, really. But you just want to make them really explicit because they're what's going to matter for determining how representative the sample group is. Third step, identify the margin of error. We'll talk about that a little bit more later. And then lastly, evaluate the argument. And the way you sort of focus on evaluating these arguments for our purposes, our non-math purposes, you're going to look for two fallacies. The fallacy of hasty generalization, which we've already talked about, and especially the fallacy of biased statistics, which is the new one that's getting introduced today. Hasty generalization is where the sample group is so small that it is impossible for the sample group to represent the overall population. If I want to represent all Americans with 2 people, that's just impossible. However careful of a job I do picking those 2 people out, those 2 people will not represent all Americans. There's just too much diversity amongst Americans for that. In general, don't worry about hasty generalization too much here. Again, like I said, you can actually calculate exactly how large the sample group needs to be. Frequently, it's dramatically smaller than you would guess. That's why like you kind of aren't in a position unless you're really doing math to gauge it. 500 people could be enough to represent all 300 million Americans if you pick those 500 well enough. You have to pick them really well. But if you pick them well enough, 500 could be enough. Right? So your intuitions about how large or small things need to be aren't super reliable. So mostly just don't worry about it. The other fallacy to look for, this is the one that you should focus on, is the fallacy of biased statistics. So here. This is there some, what the bias in this case means, is there a systematic sampling error built into the method that was used to assemble the sample group such that a relevant group is being excluded from the sample? That's what we mean by bias in this case. It's not necessarily like I'm being prejudiced or something. It's just I screwed something up in how I selected people, maybe because I was prejudiced or maybe just because I screwed something up. And as a result, sort of systematically left people out of the sample group that needed to be there. So that's the sense in which there's a bias. Someone who should be there is being excluded, right? For systematic reasons. That's the main thing to look for. If the argument is avoiding the fallacy of biased statistic, mainly you'll just want to say, yeah, it's probably a strong enough argument. Right? Relative strength or weakness, again, we just have to do too much math to actually figure that out. So that's enough for our purposes here. All right. So any questions just based on that little introduction? All right, now I'm going to give you a little bit longer because, like I said, there's more to do here. So try to work through all 4 of these questions with number 7, and then we'll talk about it together. And I might go stretch for a minute, so I'll be right back while you're doing that. All right, let's start working our way through these problems. So first, what's our sample group and our overall population? So our sample is the people who responded to, not all 3,000 of these people, because all 3,000 of them didn't respond, but the people who responded of those 3,000 people. Okay? And those people are people who are emailed and called. And that's useful, right? Not just people who are emailed, because maybe that leaves out people who don't have computers. Not just people who are called, that would leave out people who don't have phones, maybe, right? So yeah, so all of that is sort of useful, relevant information to bring up in defining what the sample group is. What's our population? It's all adult Americans. Right? Presumably, not necessarily even just ones who vote or whatever. That would be a different issue. This is just all the adult Americans are supposed to be represented by the people who responded from these 3,000 adults. And it's worth noting we're not told exactly how many of these 3,000 responded, though we know it has to be at least 100, because that's how many you would need to get 53%. You would need exactly 100 for that. That's at a minimum. All right, what was our sampling method? So go to our second question. Sampling method is what's called stratified random sampling. And this is sort of the best practices, the best technique. If something's using this, it's probably going to do pretty well for itself. So let's go through both of the two sides of it. So what I mean by the random side and the stratified side. So the random side, we just mean that people were selected at random. But the people running this survey didn't individually choose people. They used something maybe like a random number generator. They picked names out of a hat, something to get people, right? And that's valuable because if you want to put it this way, randomness doesn't have any biases. It's sort of a goofy way of thinking about it, but like a random number generator doesn't actually have biases, can't make mistakes in who they select. It's just happening at random. So you sort of, by using randomness, you sort of eliminate the worry that some bias on the part of the selectors is tilting the scales a little bit one way or the other. The downside of randomness is that it raises the possibility you could just get unlucky, right? So that's why we do the stratification on top of the randomness. That just accounts for the unluckiness factor in a sense. So we can be more specific with this. So we're talking about Medicare. That's our topic here, right? And I imagine most of you would agree with me that there are probably meaningful differences. It's not all or nothing, but there's probably meaningful differences in proportions of people who like Medicare or are in favor of Medicare being the way that it is, and who are really, really rich versus who are really, really poor. There are probably differences amongst those two groups, right? Or maybe who are older versus who are younger, or who are Democrat or Republican, or again, keep going, right? Man, woman, live in some states rather than other states. I mean, we can just keep going with all of these differences, and we would suspect, just based on our background knowledge of Americans, that those demographic factors are going to be relevant in how people might feel about this question. And again, that's not to say that all old people feel the same way or whatever, right? Or that doesn't say that all young people feel the same way. It's just that maybe like the concerns of people who are older are different than people who are younger, and so their answers might statistically lean in different directions. If the sample group is going to represent the whole population, all of that demographic diversity should be then contained within the sample group. The concern with randomness is that you can just get unlucky, though. So let's just use this as an example. I think it's something like this. It's probably not exactly the right number, but it's something like 35% of Americans are registered Republicans, and something like, I think it's like 40 are registered Democrats or whatever, right? Like a lot of people don't vote, and not everyone votes how they register. But it's something like that. It's something like 35% for registered Republicans. So okay, if that's true, yeah, it doesn't exactly right, but let's assume something like that's right. It would be a big problem if, by just sheer bad luck, when I was pulling names out of a hat, I only got 10% people who are registered Republicans, right? My sample group wouldn't represent the whole population, because the whole population isn't just 10% people registered Republicans, it's 35%. Right? And so how can I correct for that? That's what I can do with stratification. Right? I can weigh those 10% that I got as if it was 35% of all the responses that I got, right? So then that proportion is being sort of treated as it ought to be. I can do the same thing again with gender, with race, with class, with where you live, and all these different factors. Try to make the demographics of my sample group by weighing things, basically. That's basically what stratification means. You just weigh how many the responses you get differently so that it matches what you think is true about the overall population. Sort of pre-existing demographic information that you possess. So that's sort of the best practices. The randomness kind of eliminates certain danger of biases, and then stratification sort of eliminates the risk of getting unlucky. So pause for a second here. Any questions with either of these first two steps, or what I mean by stratified randomness and why it's valuable, why it's sort of the best methods? That's why, by the way, it's possible to maybe even get away with as few as 500 people. It'd be pushing it, but that's if you really stratify the hell out of those 500 responses, you can get useful information maybe with as few as 500 people. Because what matters is really not the number in relation to the overall population, but the number of people in relationship to the demographic information of the overall population. There's some things where a sample size of 1 is good enough. If there's no diversity, if it's, do I like M&Ms? All M&Ms taste exactly the same. Eating one of them is enough, right? How many Americans are there? An enormous demographic diversity, so therefore the number has to be larger. Good so far? Any questions so far? All right, let's move on to the margin of error now. So let's move on to this third question. So in this case, the margin of error, the way you usually get to put it, it's plus or minus 3%, right? So we're told sort of exactly 53% of people in the survey group, in the sample group, held the belief. They could have just said, so therefore exactly 53% of all adults believe this, but they're adding in this wiggle room, this margin of error, this plus or minus 3% from that 53 number. Let's pause for a second and just talk about margins of error a little bit, because they kind of work counterintuitively. And this is another place where I sometimes see students sort of go wrong. So I actually want you to answer this question. So you can either unmute yourself or do it in the chat. But I actually want you to try to answer this, at least a few brave people anyway. If on the exam, hint, hint, you're going to see this on the exam. If I asked you as a question, does the larger margin of error make an argument weaker or stronger? How would you answer? So larger margin of error, weaker or stronger argument as a result?
Wouldn't it make it weaker?
Vote for weaker. I'm getting a couple votes in the chat for weaker too. Excellent. That's not right, but that's why I wanted you. If someone just added in strong. That's why I wanted to do it though, because the way this works is counterintuitive. So that's why I really wanted people to go out for it. And what Cody is saying in the chat is exactly right. Let's try to explain it now. Let's try to talk it through. Because it is counterintuitive, right? How can making the error bigger make a stronger argument, right? That doesn't make any sense. That's super counterintuitive. Here's maybe a way of thinking about this. So we can do a simpler example. There are 14 of us in this room right now, this Zoom discussion. If I was to predict exactly one of us has a January birthday, right? And I would be the one because I have a January birthday, how likely is it that I'm right? Well, we could calculate it, but let's not worry about that, right? What would make me wrong? What would be enough to make my prediction wrong? If a single one of you had a January birthday, my prediction is now wrong, right? So my prediction is very exact, but it can be proven wrong really easily as a result, right? Being exact makes it falsifiable quite easily. But now let's say I said instead of that, okay, one or two of us have a January birthday. My odds have gone up now, right? Now one of you could raise your hand and be like, well, I have a January birthday and I'm still right. I haven't been proven wrong. That was me adding a margin of error to my prediction. I gave myself wiggle room, in effect, by not being as precise, weirdly. I wasn't as precise, and so therefore there's more space for me to be right. You can think of it like, let's go back to our example, right? Like, exactly 53% of Americans, that's super precise. 50 to 56, that's a lot less precise. There's a lot of wiggle room for small errors without changing the truth of the conclusion. That's kind of what the margin of error does. The margin of error works as basically giving yourself, or giving the person making the argument, giving themselves wiggle room, right? Giving themselves space to still make a prediction, but not have to be exactly right, just right within some general range. Okay. Now, let's go back, though, to that first example. All right. Let's say I was to make the claim, there's 14 of us. 1 to 14 of us have a January birthday. Well, now I'm really likely to be right. Right? But now my prediction is useless. My prediction is now so vague, so indefinite, right, that it's just dramatic. It's become completely useless. I effectively haven't made a prediction at all. Right? There's no way for me to be wrong anymore because I know I'm a January birthday. Right? So if we go back here, right, 50 to 56, that is a weaker prediction than just predicting exactly 53%, but it's a stronger argument. What we mean by a stronger argument, so this is the key, remember this is what we mean just in general with inductive arguments. What we mean by a strong argument is that the conclusion is more likely to be true. This conclusion is more likely to be true than if we had predicted exactly 53% of Americans would believe this. And so therefore the argument is stronger, but it's less precise of a conclusion. Yeah, exactly right. And like Evo's saying, right, if you make your prediction vague enough, you can even get 100% chance, right? If let's say it was like 0 to 100, let's do the same thing that here. If it was 0 to 100% of all American adults would be opposed, I guess that's become a deductively certain argument, right? Those somewhere within that range is the option, but it's so vague that it's absolutely useless. Right? Similarly, even if we made it a little bit bigger, usually what pollsters will try to aim for is something like 2 to 3% for the margin of error. That's still usually precise enough that you get some useful results. If this had been even just plus or minus 10%, so somewhere between 43% and 63%, that's pretty useless, right? Even that plus or minus 10% doesn't give us any useful information anymore. That's something from a majority would oppose to a majority would support. Right? Or similarly, if it was a presidential election, right? If you like, I think this is the example I used in the video. I think, right? If it was like 43% to 63% of people tend to vote for Hillary Clinton in the election, great. That gives me no useful information whatsoever. That's everything from she overwhelmingly loses to she overwhelmingly wins. Not a useful prediction. So that's sort of what needs to get, that's how these arguments will try to sort of balance the margin of error. It is the case that the larger they make the margin of error, the more likely the conclusion is to be true. And so the stronger the argument becomes, but it just becomes less useful the larger it gets to. Usually people try to aim for plus or minus 2 to 3%. That's the range that people usually try to hit. So is this go okay? This helpful? Clarify it for people why precisely how margin of errors work, what the relationship is. Any other questions? There's a related concept called sampling error. That works like you'd expect. Sampling error is basically just how likely it is you got really unlucky. The larger the sampling error, the worse the argument is. But that you basically, people use margin of error to try to correct for sampling error. That's why you larger margin of error, less likely sampling error will affect you. Good. Any other questions? Like I said, hint, hint, you're going to see that question in the exam. All right. So if everyone's good, now let's get to our last step, the most important step. Let's actually evaluate the argument. Let's go to the fourth part. In this case, overall, I would say this is a pretty strong argument. Again, we can't say exactly how strong. We need to do math for that. But this is a pretty strong argument based on the information we have. Right, and why? This is, you should always say something to this effect because this is the only thing that matters. Why is it a strong argument? Because there is good reason to believe that the sample group will be representative of the overall population because of its sampling method. Right? If you can say this sentence, you are probably looking at a strong argument. If you can't say this sentence, you're looking at a weak inductive argument. But this is the sentence that sort of defines what makes these arguments strong or weak. Right? So let's talk our way through why a little bit. So we don't know exactly how many adults responded, right? We know it has to be at least 100. Right? Because otherwise you can't get 53% without 100 people. 53 is prime. Right? So okay, fine. But as a result, is 100 people enough? Well, that's probably a little low. But we can, we have reason to think at least that enough people responded that this is probably good enough, right? It's probably large enough. Again, don't worry too much about this, right? We don't have any egregious reason to think that this argument's committing hasty generalization fallacy, right? Even if our response rate is maybe like 20%, that would probably be enough that we could at least get some useful information out of it. So again, minor concern, don't worry too much about hasty generalization. I'll just say straightforwardly, I'm not going to give you a problem where the answer is this argument commits the hasty generalization fallacy. You would just have to do math to determine that, so just don't worry about that one. Is there a bias? Has the fallacy of bias statistics been committed? That's the more relevant one. That's the one to worry about. Okay. The only bias that this sampling method introduces is that, but again, reiterate what I mean by this. What I mean by bias, I mean the only people who are systematically excluded from being included within the survey are people who choose not to respond. People who will not respond to surveys, they are not included by definition in this sample group, right? And let's pause for a moment. That actually might not be a trivial concern. There's not much we can do about it, right? I mean, it would be a super big problem if, like, I hold you all at gunpoint and force you to answer your student evaluations for this year. Right? I shouldn't do that. That's not a good idea. That's not right. Right? So as a result, the only people I'm ever going to be able to get to respond to me are people who choose to. Right? Could that be a problem? Well, it depends. Are the people who choose to respond weird? It's a weird, but I don't mean weird. I don't mean weird in a problematic sense. I mean weird statistically, right? If the people who choose to respond to these things are meaningfully different than people who don't choose to respond to these things, that is potentially a problem, right? Let's do this. Feel free to say it just in the chat or whatever, right? Like, I actually I'm always curious to see this. Would any of you pick up a phone call from a random number you don't know? And even if you did, would you, if they wanted you to fill out a phone survey, would any of you do that? A single person? Yeah, I've yet to see a single yes. And this is the last group. So of the 90 people I'm teaching logic to, I've yet to get a single person say yes, they would. What does that mean? It means all of you are systematically excluded from the results of any of these surveys. You and people like you will never show up. You and people who choose not to respond will never show up, right? Same thing with email surveys, right? Email surveys, my guess is probably maybe a few of you would respond to an email survey, maybe a little bit higher of a percentage. I think last year I got 5% of students responding to my student evaluations. Try to do better this year. I like student evaluations. I find them super valuable. Try to do it for me, if nothing else. But yeah, it was like 5% last year that I got of students to actually respond. So that's not zero at least, right? But if those people who chose to respond are really different than the rest of you who did not choose to respond, that could be a problem. Right? Political pollsters are increasingly worried about this problem. The last two presidential elections, the last one wasn't that bad, but the polling for the 2016 election was a little bit off. It's not as off as people were talking as if it was, but it was still a little bit off. And people who do this for a living basically were trying to figure out why was the polling data off. One worry that people have increasingly raised is that the number of people who respond to these surveys is getting increasingly small. And the people who respond might just be a little bit weird. And again, I don't mean weird like in a bad way, right? I just mean weird statistically. Like they're just like statistically abnormal in some sense. You might have heard people say this. I don't believe there's any actual evidence of this. There's some thought that maybe conservatives are less likely to answer these things than liberals. That would obviously be a pretty big problem if we're trying to do political polling. I don't believe the evidence supports that from what I've read from people who do this for a living. There actually doesn't really seem to be evidence of that. It's a little bit more of a subtle distinction of who responds versus who doesn't to these things. It more corresponds with things like how trusting of a personality you are actually. Like people who have like a super trusting personality are more likely than people who are less trusting. So that doesn't neatly break liberal conservative exactly, but that could be meaningful though. That could be a meaningful information in terms of how someone's likely to vote in a particular election. So this is something to notice. It's something to mention, to bring up. But let's go back to the problem. Again, unless we're going to hold people at gunpoint, this is an unavoidable worry, right? There's nothing we can really do to overcome this potential bias that doesn't break laws or whatever, right? And maybe you could try to like pay people to do it, but that introduces its own biases, right? That would introduce its own limitations. So since I don't see any other bias, at least besides this, because of the stratified random method that was used, this is the only bias that we can see, and there's no way to avoid it. It seems that the fallacy of bias statistics has indeed been avoided. Right? there's no at least avoidable systematic error introduced into the sampling group. So as a result, we can conclude that this is a reasonably strong argument. And again, exactly how strong is it? We'd have to do math for that, but that we can at least derive useful information from this poll. All right, how are we doing? Is this any questions with anything that we were just going through or talking about? Any questions with this problem? All right, let's do one last example. So I have one more of these inductive generalizations to do. So why don't you work through number 8? Again, take a minute or two. All right, so let's start working our way through this one. So first, begin just identify our sample group and our population. So our sample group is these 96 actor athlete owned restaurants, right? And our population is sort of all restaurants, or if you want to put it this way, all newly opened restaurants. I would accept either answer on the exam. Either answer would be fine. And the reason is they both kind of mean the same thing. Every restaurant was a newly opened restaurant at some point. So they sort of collapse into one another in this particular case. So either answer would be fine. The way the conclusion puts this in terms of sort of new restaurants, but if you adjust it all restaurants, that's right too. They sort of mean the same thing in this case. What wouldn't be right is saying if the population was all new businesses. That's not okay. This 33% of all new businesses number, this Restaurant Advocacy Monthly is not deriving that number. We don't know where this number is coming from. They must have found it from somewhere else. They're not discovering that giving their survey. Their survey is looking at restaurants and then comparing restaurants to other businesses. So it's all restaurants or all new restaurants as their population. Any questions there? Everyone good so far? All right, let's go down to our question of the sampling method then. In this case, right, we don't really see there's no randomness was employed at all, nor was any kind of stratification employed. So we are not looking at best practices. The magazine just chose 96 restaurants to look at. They chose them sort of specifically. Right? No random number generator, no picking out of a hat, anything. Now, that's not best practices, right? That's not the best method, but in and of itself, this does not mean that we're looking at a bad inductive generalization. It's really hard and expensive to do this. Right? And that's how like the Wall Street Journal maybe can afford to, but like it takes a lot of money, it takes a lot of time, it takes a lot of resources, and it takes a lot of researchers to do a true stratified random sample. Right? It's difficult. Not everyone can do it. So a lot of the time, people will have to rely on sort of second best or third best. I mean, this is definitely probably third best methods to try to do as best as they can given their constraints. So in and of itself, this doesn't make it a bad study, but it does introduce dangers. It introduces some risks. And so what we'll need to look for is, have these risks been avoided, or did they sort of stumble right into them? And the risk is that there'll be some bias seeping in the person or group who made the selection. Again, we don't necessarily mean like consciously, right? But just that there's some mistake that they made that led them to exclude certain parts of the population from their sample group. right? Or maybe to overrepresent certain parts of the population within their sample group. So if we see that steps are being taken to minimize that risk, we could still be looking at a fine argument. Whereas if we're not, if there is some sort of systematic bias excluding certain kinds of restaurants or underrepresenting certain kinds of restaurants from our sample group, then we'd have a problem. We'd have the fallacy of bias statistics. Before we get to that right away, we can talk about the margin of error briefly. In this case, there's not really a margin of error that's given. So you could just say there isn't one, or not one, or not a mathematical one, maybe. You could maybe say that there's kind of a margin of error here, right? So what would be the exact prediction? The exact prediction would be 13% safer, right? Because we're told that from our sample group, 20% closed. Overall, all restaurants, 33% of them closed. So the exact prediction would be like it's 13% safer, right? Whereas the conclusion is just that it's quite a bit safer. So I guess you could sort of call that kind of a margin of error if you like, whatever the difference is between 13% and quite a bit safer. But that's not a number. That's not really like a mathematical calculation. And so for our purposes, we can just sort of dismiss that. That's not, it's enough here to just say there's no real margin of error. Any questions there? All right, so let's get to our last step then, evaluating the argument. Has this danger been avoided? Sadly not. Sadly, I don't think the danger was sort of walked right into in this case, and this argument commits the fallacy of bias statistics. Again, what does that mean? The actor and athlete-owned restaurants are not representative of all restaurants. Again, that's sort of like just defining it, right? That's what we mean here, right? Why not? Why are they not representative? They have various advantages that the other restaurants don't. Right? Maybe they're owned by wealthier people, and so wealthier people can afford to operate at a loss for longer. Maybe they have the actors and the athletes, they have larger social media presences, so it's easier for them to advertise, right? Or maybe bring in other famous people or bring in other investors. Who knows, right? It's enough. There's various kinds of advantages that you could imagine that they would have that restaurants that are not owned by actors or athletes would not have. And so since this sampling method has only allowed in restaurants with those advantages, yeah, it's therefore not giving us any reliable information. They didn't do their math right? Their method wasn't sound enough to arrive at the conclusion that they're trying to arrive at in a mathematical way. Is it also committing hasty generalization? Probably not. Again, 96 probably would be enough if you picked them well enough. It's right, but you don't even need to worry about that in this case. It's enough to just say fallacy of bias statistics. Get rid of it. Bad argument. All right. So any questions with this one? All right, I'm going to give you one more example of the fallacy of bias statistics, just because it's a really funny one, and I really enjoy it at least. I hope you do too, but I really enjoy it at least. So this was a real, from what I'm told, this is a real enough story. It always shows up in logic textbooks, probably exaggerated. But in the early 90s, there was a study done to try to figure out how dangerous car crashes were. And their method, the method they sort of used, was that they sort of basically just like talk to people who had been in car crashes. Right? And they concluded as a result of their study that car crashes didn't really seem to be that lethal because almost no one they talked to died. And what's the obvious mistake? The dead can't join in. Right? And they figured, I think they figured this out before they tried to publish it or anything. But like, it's just a great example of like how their sort of method systematically excluded people who really needed to be there, right? Systematically excluded those who had died. Probably not even those who had died. Probably even a lot of people who had just been severely injured. Probably couldn't even get to them, talk to them too, right? If they had been, say, paralyzed or something, maybe they wouldn't have been able to do it. So that's another example, I think a funny example, right, of how sort of the way that you sort of go about selecting your sample group can systematically exclude certain people who are in the population from your sample group. And so therefore be unrepresentative. And that's what I want you to sort of be on guard for with this fallacy of bias statistics. And that's the big thing I sort of want you to look at in these problems. Hasty generalization, again, you need to do too much math to really know that. You can sort of recognize at least really obvious mistakes with fallacy of bias statistics without going into sort of mathematical rigor. So yeah, so any questions with anything we've talked about today? All right, then I think that let's end it here. My neck will be grateful to end it here, I think too. So that's good. Yeah, the exam this weekend will be a little bit shorter, like I said. It'll cover the chapter 6 material, statistical syllogisms. Remember those about one sentence, maybe two at most sentence for the statistical syllogisms. Make those short, and then a longer, sort of more full paragraph kind of descriptions for the inductive generalizations. Yeah, and then I'll try to, hopefully, my neck is definitely getting better, so hopefully by the weekend I'll be able to start trying to get some grading done, try to get caught up with that there. Yeah, and then we'll start winding the semester down a little bit. The last week is the last time we're going to do one of these in-class activities. We're not going to do one the last week, and we'll slowly, gradually start winding down to the end of the semester. The final exam is actually probably going to be pretty short, I would guess. Yeah, so that's it for me. So I hope you're all doing well. Came back at least a little bit rested, a little bit recuperated from the break, and I will talk to you all next week. Have a good one.
Thank you.
Absolutely.
Thank you.